Hello viewers, this is Big Jack, the physics tutor, and in this representation I'm going to answer physics under length and time. To start with, the question is saying figure 1.1 shows a measuring device. So we have this measuring device. So the first question, which is question A, is saying name this measuring device. So the name of this measuring device, it is called the micrometer screw gauge. So it is called micrometer screw gauge. That's the name of this device. So whenever you see something like this one here, just know that this one is the micrometer screw gauge. And then as for question B, it is saying, what is the reading shown on the device? What is the reading shown on the device? So to know the reading here, there are some things that you need to consider. So this scale here that I've circled with the red color, it is called the main scale. And this scale here that I've circled with upper green, it is called the rotating scale. Right. So let's start with the main scale. So as for the main scale, we have the scale like this one here. Suppose you have been given something like this one here. Let's say this one is 0. What you need to know is that each line in the main scale represents 0.5. Each line in the main scale represents 0.5. Which means if this one here it is 5, the next dot here is going to be 5.5. Then the next one here is going to be 6. That is what it means when I say each line in the main scale represents 0.5. So how to take the readings in the main scale? It is like this. Just take the reading which is closest to the rotating scale. So it is this one here that we are going to take. Now, since I was saying each line represents 0.5, so if this one here it is 5, the next one is going to be 6, 7, 8, and this one is going to be 8.5. So as for the main scale reading, we have 8.5. Then let's come to the rotating scale. As for the rotating scale, you need to get the reading where the line from the main scale and the line from the rotating scale are colliding. So in this case, like the way they brought this question, the lines were not colliding, but we have this one here, which is near to the line of the main scale. So we can just take this one. So now if this one here is 20, the next one here is going to be 21, and our final answer is going to be 22, right? Because this one is 20, 21, then 22, this point here. So we have the rotating scale to be 22, right? But there are some things also that you need to know when taking the final reading or the readings. So let me just give you the formula. So final reading is equal to the main scale reading, right? So we have the main scale reading plus the rotating scale reading multiplied by the accuracy, right? Multiplied by the accuracy. So in this case here, you need to know the accuracy of the micrometer screw gauge in millimeters and also in centimeters. So the accuracy of the micrometer screw gauge in millimeters, it is 0.01 millimeters. That's the accuracy of the micrometer screw gauge. Then let's come to the centimeters. So as for the centimeters, it is 0.001 centimeters. That's the accuracy of the micrometer screw gauge. Now in this case here, we haven't been given the units to use. In most cases they include something like, if they say millimeters, which means when you're taking the readings here, you need to use the accuracy of the micrometer screw gauge in millimeters. And if they include here centimeters, you need to use this accuracy here. So now in this case here, we haven't been given the units here. So always when you are calculating the readings on the micrometer screw gauge, if they haven't indicated the units on the device, you need to use the accuracy of the micrometer screw gauge in millimeters, always. So let's do that. So we are finding the final reading. So final reading is equal to, so the main scale reading, it is 8.5, then plus the rotating scale, it is 22 multiplied by the accuracy. So I was saying, always when you haven't been given the units to use on the device for the micrometer screw gauge, you need to use the accuracy of the micrometer screw gauge in millimeters. So the accuracy of the micrometer screw gauge in millimeters, it is 0.01 millimeters. Right. So here when I multiply, I'm going to get 0.22. So we have 8.5 plus 0.22 millimeters. So when I add here, or when I do the computation, the final answer is just going to be 8.72 millimeters. So on this part here, you need also to include the units. Units are very, very important. Right, so this is how you answer the final reading, or the readings on the micrometer screw gauge. Just get the reading which is closest to the rotating scale. Then after that, for the rotating scale reading, you get where the lines are colliding. So in this case here, as you can see, the line which is closest to the line on the main scale, it is 22, right? So question C is saying, state 2 precautions to be taken when using this device. So the first precaution is going to be, you need to zero the instrument, right? You need to zero the instrument before taking any reading. You need to zero the instrument. Then the next one is going to be rubrico the moving parts. You need to rubrico the moving parts. Then the last one is going to be, you need to clean the anvil and the spindle, right? So those are the precautions that you need to take. Question 2. Figure B1.1 shows part of a micrometer screw gauge. So we have the micrometer screw gauge here. So the first question is saying, what is the reading on the micrometer screw gauge? So here, even on this part here, they haven't given us the units like millimeters or centimeters. So when you haven't been given the units, you need to use the accuracy of the micrometer screw gauge in millimeters. So we have the final reading is going to be, what is the reading on the main scale? So the reading which is closest to the rotating scale here, it is 20. So we have the main scale here, which is 20 plus. What about the rotating scale? So here we can see that the line from the main scale and the line from the rotating scale are colliding at 30. So it is 30 here. Then multiply by the accuracy. So the accuracy here, it is 0.01 millimeters. Right. Then after that, our final reading is just going to be 20.3 millimeters. Of course, here you're supposed to use a calculator, so you need to use a calculator here when doing the computation. Then as for Roman numeral number 2, it is saying state one use of a micrometer screw gauge. So the micrometer screw gauge, it is used in measuring small length, right? It is used to measure the length of smaller objects. For example, the length of a wire or the length of the air, right? So those are the answers for Roman numeral number 2. Question 3. Question 3 is coming from the vernier calipers, and the question is saying figure B1.1 shows part of a vernier calipers. So we have on top here the vernier scale, and down here we have the vernier scale. So the main scale and the vernier scale, right? The first question is saying what is the reading of the vernier calipers? So similarly on this part here, since here we have two scales, we have the main scale and the vernier scale, so we can just say the final reading is just going to be the main scale reading plus the vernier scale reading in this case here. So this part here, we are just going to consider the vernier scale reading, not the rotating scale, right? This one is different from the micrometer screw gauge. So here we consider the vernier scale, right? So we have the vernier scale multiplied by the accuracy. So in this case here, how we take the main scale reading is like this. You take the reading on the main scale before the 0 on the vernier scale. So we have the 0 on the vernier scale here. Now, just before the 0 on the vernier scale. So on top here we are having the main scale. Now, to take the readings on the main scale, just take the reading before the 0 on the vernier scale. So before the 0 on the vernier scale, it is this one here that I have circled. So now what number is this one? So how are we going to know that number? We need to see the number here. So this number here, it is what? It is 8. Then from there now, as you can see, the way they are counting the numbers here, they lay out. If this one here is 8, this one is going to be what? 9. So how many lines are here? They are how many? They are about, starting from 8 up to 9, they are about 10, right? Yes. So which means the number here is just going to be 7.9. So somewhere here we are having 7, okay? Somewhere here we are having 7, and this one is going to be what? 9. 7.9, okay? Yes. Then 7.9 plus 1, you are going to get what? 8, which is this one here. So the main scale reading, it is 7.9. So here we have been given the units to use, which is the centimeters, okay? Plus, as for the vernier scale reading, also here you take the reading where the line from the main scale and the line from the vernier scale are colliding or are meeting. So it is at this point here. Now we're going to know that this number is this one. So if this one here is 0 and this one here it is 10, which means each line in the vernier scale is representing 1. So we have 1, 2, 3, 4, 5. So it is at 5 where the lines are meeting or are colliding. So we have 5 multiplied by the accuracy. Now on this part here, the accuracy of the vernier calipers and the accuracy of the micrometer screw gauge, these two are different. So as for the vernier calipers, the accuracy of the vernier calipers in millimeters, it is 0.1 millimeters, right? That's a difference. Then apart from this one, we also have the accuracy of the vernier calipers in centimeters, which is 0.01 centimeters, right? So these are the accuracy of the vernier calipers. First one in millimeters and the second one in centimeters. Now since here we have been given the units as centimeters, which means we are going to pick this one here, the accuracy of the venial caliper in centimeters, which is 0.01 centimeters. So here we are going to say 0.01, then we put centimeters here, right? So when I do the computation, the final answer is just going to be 7.95 centimeters. Even here you are supposed to include the units. So that is our final reading, or the reading of the venial calipers. Then as for question B reads, write in words and SI units of the following physical quantities and state their symbols. So in talk of physical quantities, these are measurable quantities, the quantities that you can measure. So we have the first one, which is the velocity, right? So the velocity is measured in meter per second. So in form of a symbol, we say meter per second. So now where is this one coming from? This one is coming from this formula here. We know that velocity is equal to displacement over time. Now what you need to know here is that distance is measured in meters, then time is measured in seconds, and this division is same as pair, right? Division and pair, they are just the same. So if I write something like this m here, we have m, then division here I'm going to put pair, then here we have s, we are going to put s. So this one is meters per, or meter per second. That is where the units for velocity comes from. Then as for Roman numeral number 2, the SI units for temperature. So the SI units for temperature are kelvins. Kelvins denoted by capital letter K. So temperature is measured in kelvins, not in degrees Celsius. Okay? It is measured in kelvins, not in degrees Celsius. When I say it is not measured in degrees, which means the SI units for temperature are kelvins, but temperature can be measured in degrees Celsius, but the SI units for temperature are kelvins. Then we have acceleration. So as for acceleration, is measured in meter per second squared. Meter per second squared. So this one is coming from this one here. Since we know that acceleration is equal to the change in velocity over the change in time. So here velocity is measured in meters per second, or meter per second. Then time is measured in seconds. So what we are going to do here, since pair is more like division, so when I write something like m divided by s, these are the same as this one here, right? Then from there now, this one is division. So when I say divide, then we have s here for time. So I'm going to say divided by time. Now division, there is pro of division. It is multiplication, right? That is the discipline. So here we are going to have m over s multiplied by, so here it's more like we are having s divided by 1. So when division changes to multiplication, what happens is that the quantities or the figures that we are going to have on the right hand side, they are going to explore each other. So which means on top here I'm just going to have 1, then down here I'm going to have s. So m multiplied by 1, we are going to get m. So we are going to get m over s multiplied by s, we are going to get s squared, right? Now since division is same as pair, which means this one can be written as meter per second, squared. So that is where now the units for acceleration, or the SI units for acceleration, comes from. So here we have meter per second squared. So the next one is saying the figure below shows an experiment which was carried out to measure the time interval of a simple pendulum. So say the simple pendulum is used to measure the time interval. So we have the bulb, the cotton thread, which is also known as the string, and also the support, also known as the fixed point. Now, for one complete oscillation to be made, the bulb needs to move from A up to C and back to A. That's the complete oscillation. Right. So, we have the question. The bulb was oscillating between A and C. So from A up to C. So we can just show this one as like this. State the meaning of the term oscillation. So oscillation is the complete swing of the pendulum bulb. So oscillation is defined as the complete swing of the pendulum bulb. So when you say the complete swing, if this one here is the pendulum, here we are having A, B, and C. For one complete oscillation to be made, the bulb needs to move from A to C and back to A. This one here we are going to call it as one complete oscillation. And usually, the number of oscillation are represented by small letter n. So small letter n denotes number of oscillation. So B is saying if the pendulum bulb took 0.20 seconds to swing from A to C. So the bulb swing from A to C. Calculate the period of the pendulum. So here we need to calculate the period. So the period is also known as the period of the pendulum. Now, I was saying the bulb is going to make only one complete oscillation when it moves from A to C and back to A. That's one complete oscillation. But here they have said the bulb has moved from A up to C. Now, is this one going to be one complete oscillation? No, unless it moves from A to C and back to A. That one is going to be the complete oscillation. So, let me show you how to find the oscillation when the bulb haven't completed one oscillation. So, in this case here, suppose we have the pendulum, which is this one here. Suppose we have the pendulum, which is this one. So this one is A, this one is B, and this one is C. So how many moves does the bulb going to take for each to make one complete oscillation? So how many moves? Let's count. So from A up to B, this one is going to be 1. Then from B up to C, this one is going to be 2. Then from C up to B, this one is going to be 3. Then from B up to A, this one is going to be 4. So how many moves? Here we have 4 moves. Right. So we are going to use probability for us to know the number of oscillation for a bulb to move from A up to C. So now, since the bulb has moved from A up to C, so how many moves does the bulb covered here? It has covered only 2 moves. One move for AB, this one is going to be 1. Then from B up to C, this one is going to be 2. So it has only covered 2 moves. Probability is equal to favorable outcomes divided by the total probability. So in this case here, the total probability is what? 4. And the favorable outcomes here, it is what? 2. So what we are going to do here, for us to know the number of oscillations, we are just going to say 2 over 4. Now this one is same as half, right? This one is same as the half. which is 0.5 in other words. Now, since we know that the number of oscillation here is equal to 0.5. Now, suppose a bulb moves from A up to C and back to B. What will be the number of oscillations if the bulb moves from A up to C and back to B? What will be the number of oscillations? So in this case here, we are just going to consider the number of moves that this bulb has covered. So it has covered 3 moves. So favorable outcomes here, it is 3. Then divided by the total probability, which is 4. Then here, when you divide, you are going to get the number of oscillations. Now suppose the bulb moves from A up to C and back to A. How many moves does it going to cover? It is going to cover 4 moves divided by the total probability, which is 4. Then the answer is going to be what? 1. So that is where now 1 complete oscillation comes from. So let's try to answer the question. So here you need to know the formula. So the period of the pendulum is equal to the time taken over the number of oscillation. So you need to know that time is measured here in seconds. Then also the period of the pendulum is measured in seconds. But as for number of oscillations here, number of oscillations does not have units. So let's do this. What is our time here? So the time here we have been given, which is 0.20 seconds. So we have 0.20 seconds, which is 0.2 in this case here, divided by the number of oscillations. So the number of oscillations here that we have, it is 0.5. So this 0.5 is coming from the probability that I have explained. So the bulb has moved from A up to C. From A up to B, that's 1 move. Then from B up to C, that's 2 moves. So we are going to say the favorable outcomes, which is 2, divided by the total probability. So when it moves from C up to B, this one is going to be 3. Then from B up to M, this one is going to be 4. So the total probability is going to be 4. So divide by 4. Then when you divide, you are going to get this number of oscillations. Now, the final answer here is just going to be 0.4 seconds or sec. So this one here is our final answer for the period of the pendulum. So the period of the pendulum here, it is 0.4 sec or seconds. So let's answer C. C is saying, using your answer in P, determine the frequency of the pendulum, 2 marks. So frequency is equal to 1 over the period of the pendulum. So in this case here, the period of the pendulum, it is 0.4 seconds, right? 0.4 seconds. So what we are going to do here, since here we have 1, and the period of the pendulum here, it is we have 0.4 seconds. So when I divide here, the answer is just going to be 2.5 hertz. So frequency is measured in hertz, denoted by capital letter H and small letter Z, right? But in this case here, if you want, you can't use this formula, but they have specified here, they are saying you need to use the answer in B. But if the question is not specifying to use the answer in B, you can also say frequency is equal to the number of oscillations divided by what? Time. So the number of oscillations here that we have, it is 0.5. Then divided by the time taken here, which is 0.20 seconds. So here when you divide, you are going to get the same answer here, which is 2.5 hertz. The last one. The last one is saying, figure B1.1 below shows a simple pendulum suspended from a fixed point. So we have the screen and also the bulb Yes. So the bob is slightly put to position A and then released. State one factor that does not affect the period of the pendulum. So you need to be very, very careful when reading the question. So this question is saying, state one factor that does not what? Affect the period of the pendulum. So you need to note this word here, which is not. So the first factor which does not affect the period of the pendulum, the first one is the mass of the bob. So the first one is going to be the mass of the bob, the mass of the bob. So the mass of the bob does not affect the period of the pendulum, right? So the mass of the bob does not affect the period of the pendulum. Then the last one is going to be the amplitude. Now this amplitude, let me show you where the amplitude is. So the amplitude is just the angle. Suppose we have also a bob here. Yes, suppose we have a bob here. The amplitude is just going to be the angle from this bob here up, from this bob here. So let me just show you. From this bob here up to this bob here at N. Now on top here, this one is going to be called as the amplitude. So the amplitude does not affect the period of the pendulum. So when they say does not affect the period of the pendulum, which means when you increase the angle, the period of the pendulum is not going to be affected. Even if you increase the mass of the bob, the period of the pendulum is not going to be affected. Now, it is not always that they are going to ask you about the factors that does not affect the period of the pendulum. Sometimes they can also ask you to give them the factors that affect the period of the pendulum. The first one being is the length of the pendulum. So the first one being is the length. So we have the length of the pendulum. Then apart from the length of the pendulum, what you need to know is that the acceleration due to gravity also affects what? The period of the pendulum. So acceleration due to gravity also affect the period of the pendulum. So these are the factors also that affect the period of the pendulum. Let's come to B. So B is saying if the values of the time for 20 oscillation, so here we have the number of oscillation being equal to 20 oscillations. If the values of the time for 20 oscillation obtained were 16.1 seconds, 15.9 seconds, 16.0 seconds, 16.2 seconds, and 15.8 seconds. Calculate the period of the pendulum. So we have been given the time here, which is 16.1 and so on. So the first thing here, we need to add the time. So let's add the time. So we have 16.1 plus 15.9 plus, so we have plus 16.0 plus 16.2 plus 15.8, then at the end seconds here. So we are going to get, when we had here, we are going to get 80 seconds. Now this 80 seconds, it is not the actual time that we are going to get, right? Or that we are going to use, not that we are going to. Now this 80 seconds is not the actual time that we are going to use to calculate the period of the pendulum. So what we are going to do here, we are going to find the average. So now, how are we going to find the average? We are going to count the number of times that we have here. So we have 16.1, which is 1, 15.9, which is 2, 16.0, which is 3, 16.2, which is 4, then 15.8, which is 5. So in this case here, we need to divide by what? 5. If you have been given 6 times, like they even include 15 point something like 9, something like that, which means you need to divide by what? By 6 for you to find the average time. Now since here we just have 5 times. Okay, yes, what I mean about 5 times is like this one is going to be 1, 2, 3, 4, then 5. So if this one was on part of this one, which means we can just say 6 like that. So when I divide here, the time is just going to be 16.0 seconds. So this is the time that we are going to use to calculate the period of the pendulum. Now I want you to observe something here. When they say the average time, what does it mean? Average time is more like the time which is at the middle, right? The time which is at the middle. In Bemba we say pakati, right? So since here we are having 5 times, so we can divide, whereby we say 16.1 and 16.1 and 15.9 is going to be 2. Here we are going to have 2. And 16.2 and 15.9 here we are going to have what? 2, which means the time which is at the middle, it is what? It is which one? 16.0. So even on this part here, you can use this method or use this one here, but I prefer you using this one here to using the one that I've shown at the end here. So let's calculate the period of the. So we have the time which is equal to 16. So you need to show all your working here, even where 16 is coming from. Don't just say 16, okay? So since we know that the period of the pendulum is equal to the time taken, in this case here it is 16 seconds, divided by the number of oscillations, which is 20, then our final answer is just going to be 0.8 seconds. So this one is the period of the pendulum. Then the last one is saying, which is C, calculate the frequency of the pendulum. So we know that frequency is equal to 1 over the period of the pendulum. So in this case here, the period of the pendulum, it is 0.8. So 0.8 seconds. So when I divide here, the final answer is just going to be 1.25 hertz. So frequency is measured in hertz. Right, so that was the last one. If you see this video to be useful, share it to your friends. And remember to subscribe for more videos like this. Thanks for watching. Peace.